Hi, I'm Craig Putnam from the WPI Robotics Engineering program, and this is the third in a series of videos on op-amps. In the previous videos, we looked at different configurations, the open loop and some closed loop configurations. In this video, we're now going to start getting into more detail of the ideal op-amp model and then derive the gain equations that we saw in the previous videos. When we model an op-amp for circuit analysis purposes, we make assumptions about how the op-amp is going to operate. This collection of assumptions is called the ideal op-amp model. It's essentially how an op-amp would operate in the real world. Real op-amps will operate somewhat differently, but this set of assumptions actually generates an op-amp result, if you will, the model, that's really quite good. It actually tracks the behavior of real op-amps pretty closely. So we're not in shaky ground by making these assumptions. So what are the assumptions? We will assume that the input impedance of the op-amp is essentially infinite. Now I use the word impedance. We've called it resistance in the past. For our purposes, we'll use them essentially interchangeably. That input resistance is essentially infinite, and there's a couple of consequences of that. One is that the current that's coming into or out of those input terminals is going to be essentially zero. The other consequence is that the voltage drop across that internal resistance, the input resistance, is going to be essentially zero as well. And that means that the voltage on each of those input terminals will be essentially identical. On the output side, we have some similar things going on. We model our output impedance or resistance as essentially zero, and that allows the op-amp to theoretically deliver any amount of voltage that's necessary in order to sustain the output, regardless of what the load is. Now, again, real op-amps don't behave quite like this, but the model's actually quite good, and so we can use this very effectively in real-world situations. Before we go any further, we need to provide some more details with regards to our idealized model of an op-amp. In this picture, the components to the left of the dotted green line are the two inputs, the inverting and non-inverting inputs of the op-amp. Note that we've modeled the input resistance as the value R sub I for input. We also assume there will be some voltage drop across that resistor R sub I. We'll call that V sub in. Now, I just got done saying that that voltage drop was going to be very, very small, and we'll come back to that. Now let's connect a realistic voltage source to the two input terminals. We'll model this as an ideal voltage source, V sub S, in series with a non-zero internal resistance, R sub TH. Because the two resistances are connected in series, they form a voltage divider. As a result, we can write the following equation describing the voltage V sub in terms of the source voltage V sub S and the values of the two resistors. Now let's turn our attention to the output of the op-amp. The model shows a voltage-controlled voltage source in series with the internal output resistance R sub O. These components are in turn connected in series with some load resistance R sub L. The output voltage of the voltage-controlled source is governed by the equation A sub O times V sub in, where A sub O is the open loop gain of the op-amp. We've seen that before. Remember, A sub O is a very large value typically, essentially infinite in our ideal op-amp model. So now we can write another equation for the output of the op-amp, again using the voltage divider formula as the resistors R sub O and R sub L are connected in series. Here's what we get. Now let's combine these two equations. After a little massaging, we get the following. And from this, we can calculate the gain of the circuit. The problem here is that the gain depends on the values of all four resistors. Ideally, we want this gain to be independent of the op-amp's input and output resistances. So how can we achieve this? Well, if we let the input resistance R sub I get really, really big in comparison to R sub TH, then the first term in square brackets heads off to the value 1. And if we similarly let the output resistance R sub O get really, really small, then the second term in square brackets also heads off to the value 1. This leaves us with the following equation. Okay, so that's the equation we saw previously for the open loop op-amp. That the output is the difference in the voltages across the input terminals, which is V sub S as a function of time in this case, times the open loop gain constant A sub O. There are a couple things that we need to note at this point. The first is that as a consequence of the input resistance being so large, the current that will flow through the input resistance R sub I will be very, very small. In our ideal model of the op-amp, we will treat it as being 0. The second thing is related. If no current flows through R sub I, there will be no voltage drop across that input resistance. This is a consequence of Ohm's law, of course. Thus, the differences in the voltages V plus and V minus, the input voltages, if you will, or in other words, the quantity V plus minus V minus, that quantity will be 0. Or alternatively, we can get the fact that V plus equals V minus. With these understandings in mind, let's revisit the inverting op-amp circuit we saw in the last video. If you recall in that video, I simply gave you the overall gain equation for the circuit. That was that the gain was minus R sub F over R sub in. What I want to do now is derive that equation. To do so, we're going to need some tools. We're going to use Kirchhoff's laws and Ohm's law and some algebra. And of course, we'll be using our more detailed knowledge of the model of the idealized op-amp. Recall that there are two laws that we got from Kirchhoff. The first of these is the current law, or KCL. And essentially what that entails is a statement of the fact that all of the currents that enter and exit a node have to sum up to 0. It's really a statement of a conservation law, that you can't accumulate charge at a node. Kirchhoff's voltage law, or KVL, is accomplished by tracing a path, a loop around the circuit, any closed path. So you'll start at one point in the circuit, work your way around the circuit back to that starting point, and KVL says that the sum of all the voltages or voltage drops that you encounter going around that loop have to add up to 0. It's another kind of conservation law. And of course you remember Ohm's law, which basically says that the voltage drop across a resistor is equivalent to the product of the current that flows through the resistor times the resistance itself. We start by applying these results to the ideal op-amp model of our circuit. First, because we have grounded the non-inverting input, that forces that node to be at 0 volts. Secondly, we know that we're going to have no current flowing into or out of the input terminals of our op-amp. These two conditions taken together are called the summing point constraints. In a moment we'll see why it's been given that name. Let's focus in now on what is happening at the node that is the inverting input to the op-amp. We can see, using Ohm's law, that a current I sub n equals V in over R in is entering that node. Remember, the voltage on one side of the resistor R sub n is V sub n from the source, while the voltage on the other side is forced to 0 through our summing point constraints. Using Kirchhoff's current law, or KCL, we can also see that the same amount of current must be exiting that node through the feedback resistor R sub F. This gives us the following formula. Remember that no current can leave the node by flowing into the op-amp's inverting input terminal. We will now use the other of Kirchhoff's laws, the voltage law, or KVL. Note that when using KVL, we need to trace out the path of a loop. In this case, we are starting at the ground node, connected to the non-inverting input of the op-amp, continuing through the op-amp's input resistance R sub I through the node where R sub in, R sub F, and the inverting input of the op-amp connect, through the resistor R sub F, then finally through the resistor R sub L, which returns us to the ground node. When using KVL, we would then write down the voltage drop across each circuit element, and we get the following equation. First of all, note that the value I sub minus equals 0. And as a result, the first term in this equation disappears. Note also that we don't know the current flowing through the load resistor R sub L, so we can't use Ohm's law there to come up with an equation for the voltage drop across that resistor. But the voltage drop across that is in fact one of the quantities we use in calculating the gain. It's V sub O. So we'll just call it that and use that in the equation. We do have an equation now that involves the current I sub F, though, so let's substitute that in, and we get the following. This can be massaged a little bit to give us this equation, and from this we can calculate the gain of the circuit. Remember, the gain is the output voltage divided by the input voltage. When we do that, we get this equation, which you should recognize as the gain equation that was given to you in the last video. In this video, we've derived the equation for the gain of an ideal op-amp in the inverting configuration. We've actually covered quite a bit of ground, so we're going to leave it here for the moment. In our next video, we'll continue on to derive the equation for the non-inverting op-amp. See you next time.